Hello, good morning everyone. Thanks for joining this video conference. I'm David Diaz Arias. I'm the veterinary manager of BioVet SA, and I will talk about the use of AMN to prevent Clostridium perfringens induced necrotic enteritis in broilers. First, I will introduce AMN. This is a natural antimicrobial with fungicide and bactericide activity thanks to its main ingredients. AMN active principles are citric acid and cinnamon ring that act synergistically. Citric acid is added in the product in small quantity and it interferes with the cellular metabolism and facilitates the entry of the cinnamon ring into the pathogenic cells. Cinnamon ring, once inside the cell, it causes the immediate release of the cellular contents to the medium due to the perforation of the bacterial membrane. This leads to the death of the microorganisms. AMN is used as a preservative for both raw materials and feed, as well as a controller for the pathogens in the gut. It is an excellent alternative to organic acid or antibiotics. Let's see a trial on the effect of AMN on broilers challenged with Clostridium perfringens. The objective was to determine the effectiveness of AMN to prevent necrotic enteritis and to discern the effects of the treatments. Broilers were challenged with toxigenic strains of field-isolated Clostridium perfringens, and the diet used contained a high relative value of raw protein, around 23.5%. 160 Benko 430 broilers were used during 35 days for the experiment, and they were divided in 4 experimental treatments with 4 replicas per treatment and 10 chickens per replica. The distribution of the chicks and the replicas followed a random block design. The first experimental treatment was the negative control, where birds were fed only with the basal diet. The second group corresponded with the positive control, and animals in this group were artificially challenged with Clostridium perfringens. The third group corresponded to the treated non-challenged group, where animals received the basal diet, AMN at 1 kg per ton of feed, and finally the fourth group was the treated and challenged one, and the animals were fed with the basal diet and AMN at 1 kg per ton of feed, and also they were artificially challenged with Clostridium. The basal diet did not contain any other antimicrobial AGP nor coccidiostat. The challenge with Clostridium took place on days 14, 15, and 16, and the inoculum was obtained from samples of intestinal tissue of birds with compatible symptomatology for necrotic enteritis. Feed access was restricted for 4 hours prior and water during 4 hours prior to the challenge, and finally Clostridium was inoculated orally to each bird. 1 milliliter of cultured broth with 1 per 10 to 8 CFU per bird was administered. The following parameters were evaluated: weekly weight and daily gain, daily and weekly feed consumption, feed conversion rate, European Productivity Index, and lesions in the small gut by necropsy birds on day 22. The body weight results obtained shows a marked decrease of the body weight in the non-treated and infected group, while the best results were found in both AMN batches, challenged and non-challenged ones. The product improves weight gain even when there is no challenge because it improves and maintains the balance of the gut flora. If we analyze the weight results in the different weeks, we can see that prior to the challenge, the result remained similar. Few days after the infection, both challenged groups showed a slight decrease on the body weight, but the main differences appear from day 28 on, where we can see that the non-treated and infected group shows a marked decrease of the body weight, while the other 3 groups achieved a good weight value, even AMN infected group, which recovered the weight. These results on day 28 remained until day 35, where both AMN batches achieved the best body weight results. In the case of the average daily gain, the tendency is similar to the case of the body weight. There is a decrease of the daily gain in the non-treated and infected group, while both AMN batches achieved the best result, even better than the control. If we analyze the daily gain by phase, we can observe that the decrease on T2 and the increase on T3 and T4 are more marked in the last stage, from days 29 to 35, and have influence in the final average. Regarding the feed consumption, we can also observe a marked decrease in the non-treated and infected group, while in this case animals of T1 group, non-infected and non-treated one, achieved the best result. Both two AMN batches achieved a similar consumption with normal results. Taking into account all these results and calculating the feed conversion rate, we observe that the best values are seen in both AMN batches. The best FCR was obtained in the non-infected AMN batch, but AMN infected group also achieved a very good result. This is due to the capacity of the product for controlling other pathogens affecting the intestine. If FCR is analyzed in phases, prior to the challenge it remained similar in all the groups. After the infections, the differences began to appear, and in the final phase, there were marked differences where the best FCR values corresponded to both AMN batches, and this had impact in the total average. The worst survival rate was seen in the non-treated and infected group as expected, and the values were similar in the other three batches, even in AMN infected one, because the product is able to control the bacterial multiplication and decrease the mortality. Efficiency index was better in AMN non-treated and non-infected batch, and AMN infected batch also achieved a good result despite the infection, due to its capacity for controlling Clostridium perfringens. In the intestinal mucosa, such as gas presence, hyperemia, thickened mucosa and viscosity of the content, and finally undigested feed, were also checked, while in a scale from 0 to 3, 0 corresponds to absence, 1 to mild, 2 to moderate, and 3 to severe. We can see that with the use of AMN, a lesser degree of hyperemia and better condition of mucosa and villi are observed. Viscosity and undigested feed presence were higher in both infected groups, maybe due to the bacterial multiplication, although it did not affect the performance in AMN batch T4. Necrotic enteritis lesions were also checked with a 3-score scale, where 0 corresponded to a normal mucosa, 1 to a mucosa covered with a thin layer of mucus, 2 to a small foci of necrosis in the mucosa, and 3 corresponded to hemorrhages and foci of necrosis in the mucosa. In the results, we can observe that the worst lesion score was observed in the infected and non-treated batch with 1.7 points, while the other three treatments achieved a similar lesion scores, even in the infected group treated with AMN. This is due to the efficacy of the product controlling the proliferation of Clostridium perfringens. In the following pictures, we can observe small gut lesions after Clostridium perfringens infection 5 days post-infection. In the picture number 1, that corresponds to the negative control, we can see hyperemia despite there is no challenge with Clostridium perfringens. In the picture number 2, the infected and non-treated batch, we can see hyperemia, necrosis hotspots, and undigested food presence. In the picture number 3, the no-challenged group but prevented with AMN, we can see a mucosa with no lesions. And finally, the infected group and treated with AMN shows mild injuries, although loss of mucosal consistency is observed. Regarding the productive parameters, we can conclude that the T1 group, the negative control, shows the normal FAR parameters. T2 group, the infected one, in this group, productive parameters were greatly affected by the infection. T3 group, AMN group, showed the best productive parameters, even better than the negative control, due to the positive effect of AMN over the intestinal flora. Finally, T4 group, the infected but treated with AMN, normalized the productive parameters compared to the infected and untreated group. If we compare both non-infected batches, T3 and T1, we can conclude that by using AMN, all the productive parameters were improved. Weight was improved in 6.45%, FCR improves in 6.09%, efficiency index improves in 52.4 points, and finally, lower mortality was achieved in 2.5%. So, AMN improves productive parameters in healthy animals. On the other hand, if we compare both infected batches, T4 and T2, we can also conclude that by using AMN, all the parameters were improved. Weight was improved in 2.12%, FCRs improved in 3.93%, efficiency index improved 84.2 points, and also lower mortality was achieved in 7.5%, so that AMN prevents the negative effects of the necrotic enteritis. We also checked the bacterial flora, and both groups with AMN, T3 and T4, obtained a higher count of lactobacillus, beneficial flora, and a lower count of Clostridium perfringens. So AMN prevents the overgrowth of pathogenic flora, but it's harmless to beneficial flora. This product promotes the balance of the gut flora. Regarding the lesions in the small intestine, we can see that animals not infected with AMN show very mild and specific injuries that are avoidable with the use of AMN. Animals infected show injuries in the mucosa with necrotic foci due to the necrotic enteritis. When AMN is administered as a preventative in infected animals, injuries occurrence is prevented. As a conclusion, AMN in healthy birds improves the equilibrium of the gut flora, which has a positive impact on the productivity, and AMN in birds challenged with Clostridium perfringens prevent necrotic enteritis. So that's all. Thanks for your attention, and thanks for joining this AAAP virtual annual meeting. Please don't hesitate to contact me for further information, and see you in the Q&A session. See you.